In this video, we will talk about the limit laws. So I want to begin with some preliminary information. I want to suppose that C is a constant. So it's just going to be some real number. And let's also suppose that the limit as x approaches a of f of x and the limit as x approaches a of g of x, of those two functions, both exist. So both of those limits exist. Then we're going to have the following things. Okay, so I've started writing these limit laws, one side of the equation, but we'll fill out the other part together. All right, so the first limit law says if you take the limit as x approaches a of f of x plus g of x, that is equal to the limit as x approaches a of the first function plus the limit as x approaches a of the second function. In other words, you can sort of split the limit up. The same type of thing holds with subtraction. The second one will be equal to the limit as x approaches a of f of x minus limit as x approaches a of g of x. And then if you have the third limit law is if you have a constant multiplying the function, you can pull that constant in front of the limit and get c times the limit as x approaches a of g of x. Alrighty, so far I think all of these are kind of like what we'd sort of expect to happen. The fourth property is if you have the limit as x approaches a of two functions multiplied. And this one's also going to be, I think, what we'd expect. It's equal to the limit as x approaches a of the first function, and then times the limit as x approaches a of the second function. The fifth limit property is when you divide two functions. And this will be equal to the limit as x approaches a of the top function over the limit as x approaches a of the bottom function, g of x. The one sort of exception is we have to be mindful that the limit as x approaches a of g of x, there's one thing that it should not be equal to. It should not be equal to 0, because otherwise we'd be dividing by 0. Okay, the sixth limit law is if you have the limit as x approaches a of a function f of x being raised to the n power, where n is a positive integer. So where n is a positive integer, then this will be equal to, you can sort of pull the power all the way outside and have the limit as x approaches a of just the function on the inside. All right, so there's a few more of these limit laws that I want to state. All right, so the seventh one, it says the limit as x approaches a of c, and remember c is some constant, which means it's some fixed real number, like it might be the number 3 or the number 7.2. So before I say what this equals, we can actually explain this one with a picture. So we can actually give a reason for this one. Alrighty, so I'm going to draw an axis. Let's draw it a little bit better. So an axis, and I want to draw the graph of y equals c. So y equals c is going to be a horizontal line that goes through the number c on the y-axis. Okay, so that line will look something like this, horizontal line. And x is approaching a. So I'm going to put a tick mark at some spot and mark it a on the x-axis. And looking at this graph as x approaches a, what does the function approach? What do the y values approach? So as I approach a from the left-hand side, that's this part of the graph. As I approach a from the right-hand side, that's that part of the graph. But the y values are just approaching c. So that's what this limit should be equal to. The y values are approaching c. Property 8, I can also show graphically. This is saying, well, what's the limit as x approaches a if my function is now x? Okay, so let's give a graphical reason for this one as well. So I'll draw some axes, and I'll draw the graph of y equals x this time. And y equals x, that's a line. The y-intercept is 0, and the slope is 1. So that line looks like this. And again, I'm going to put a tick mark somewhere on the x-axis and label that as a. And I'm going to draw the point on the graph where a occurs. Maybe I should have done that on the previous one as well. Here is the point on the graph where x is a. And then when I plug a into this equation, y equals x, I know that the y value is also going to be a. So now when we talk about this limit, as we approach a, as x approaches a, from the left, the y values definitely approach a. From the right, the y values also approach a. So this limit is just a. So notice ultimately what 8 is saying is that when you have the limit as x approaches a, and your function is just x, we can essentially just plug the a in for the x, and that gives us the a. But this picture gives us a graphical reason for why that is. Property 9 is similar in that now our function is x to the n, and it turns out I can do the same type of thing. I'll be able to just plug the a in for the x, and that'll give me a to the n. I should mention here that n is a positive integer. Alrighty, and then property 10 is, well, what if our function f of x is inside of an nth root? Well, in that case, you can move the limit inside of the root, nth root, move the limit inside, and then take the limit of that function within the root. So even for this property, n is a positive integer. Alrighty, so now looking back to properties 8, limit law 8 and limit law 9 here, notice that algebraically we could sort of just plug in a for the x. It turns out we will be able to do that for some limits in general, and that's kind of our next goal. Our next goal is, how can we evaluate the limit as x approaches a of some function algebraically? That means by doing stuff like plugging in or simplifying in general situations. So there are 4 cases that we will consider. All right, and in terms of our goals for this section, we finished our first goal, to introduce the limit laws.